All right, chapter 4, section 7, the last section that we're going to cover here in chapter 4. There are a couple other sections that I decided to lop off in favor of time and that sort of thing. But for this will be kind of a good place to wrap it up, where in section 6, we just talked about complex numbers rather, which will represent this other family of possible solutions as opposed to what we talked about at the beginning of this chapter. Okay, so let's break down the title here. We're still solving quadratics, which means fundamentally, we're still doing the same thing that we've been doing throughout this whole chapter. At a visual level, at a graphing level on a coordinate grid, a quadratic represents this U shape, a parabola that we talked about all throughout chapter 3. And when we're talking about solving those quadratics, we're literally talking about where does it cross the x-axis? Because ultimately, as you can see here in these examples, when I have an equation that's set equal to something, I can fundamentally move stuff away from that x and get x equal to some value, or what we learned in this chapter, values plural. Okay, and so when we talk about graphically solving a quadratic, like what we did in section 2, we're looking for those intersection points, and there can be up to 2 for a quadratic, but there could also just be one place that it touches the x-axis, or what we learned is that it can completely miss the x-axis. For instance, if I had a happy face U shape, a happy face parabola, the happy face quadratic, that was completely above the x-axis, it's never going to touch it. Or if it was a sad face that was completely below the x-axis, it would never touch it. And since it wouldn't touch the x-axis, there would be what we would call earlier in the chapter, no real solutions. These, spoiler alert, these 4 examples right here, and this abstract one we'll talk about in a minute, but in these examples, these all will represent parabolas that if I were to plug them into Desmos and quickly graph them and see what they look like, they would completely miss and not touch the x-axis. Thus, each of these has no real solutions. That is true. Nothing about that math has changed from the previous sections and stuff. But what we're going to talk about is how to solve for what are called complex solutions. Complex solutions only exist for a quadratic when it completely misses the x-axis. Okay? There are basically 2 distinct families of numbers. Everything up until section 6 dealt with the real numbers, the tangible numbers, the numbers that we're used to dealing with. Okay? Any number that you can think of, whole number, crazy decimal, fraction, doesn't matter. They're all real tangible numbers. And from a solution standpoint here in solving for quadratics, they are real locations on the x-axis where a parabola or a quadratic will touch the x-axis. The complex number system that we talked about in section 6 that deals with imaginary numbers is not tangible. Okay, it's what we would call intangible. In other words, it does not have an actual real physical location that we can like put our hands on and touch. It's completely abstract. It's imaginary. All right. And a lot of people ask me, like, why do they exist? Like, who thought of imaginary numbers? It's advanced mathematics. And let's suffice it to say that there is an application for imaginary numbers, complex numbers in the real world. Okay. And they have to do with what are called wave functions, which is kind of above our pay grade here in Math 2. But basically things that have wave-like properties, for instance, magnetics, electricity, they have these wave properties that deal with the complex number space. It is possible to get those, and they have real-life applications. Again, this is more advanced, abstract mathematics and physics. I'm not going to get super deep into it because it would be, again, above the pay grade of many of us here in Math 2. But there is a purpose for it, and therefore, like, it's important to kind of understand where it comes from. As far as us here in Math 2, in these notes in section 7, what's the importance to us here? How do we go about solving it? For us, technically, there is only one small twist that happens when we deal with complex numbers, imaginary numbers. Nothing changes algebraically, mathematically. Okay? There will be just one small thing that we change, and that's including the letter I. I representing the imaginary number space. And I, again, in section 6, we talked about how I is equal to the square root of -1. Okay, so it has a real value, or an imaginary value, I guess I should say, but there is an actual value to I. But all of our answers, because they're complex in nature, all of these answers are going to involve an I element to them, an imaginary element to them. Because in the real space, in the tangible space, on a coordinate grid, when it comes to graphing each of these guys, it would completely miss the x-axis. So these will all have complex solutions. All right, so what are we going to do today? I'm going to only do these two C and D examples. A and B are just kind of more simplistic versions of C and D. So if you want to see these solutions worked out, they're uploaded on the solutions onto Google Classroom as well. I'm going to use similar techniques here. But we're going to be tasked with the same thing, which is to solve, or basically get x equals some values. These ones will just happen to be imaginary values. And then this guy is a more of an abstract problem, and I'll go more into that in just a few minutes. But for right now, we're just going to do these two guys, and we're going to be tasked with the same thing that we've been doing all throughout this chapter, which is to solve. So what does it mean to solve a quadratic? It means literally we're looking for those x-intercepts. Now, again, spoiler alert, these ones will have no x-intercepts, so we're going to be getting imaginary solutions. All right, so our first quadratic we are tasked with solving that I'm going to cover today is part C here, which is we're given 5x squared minus 4x plus 1 equals 0. All right, so a couple things to point out. First off, this is in standard form, just like all the other quadratics that we've come to know and love in this chapter, where we have an x squared term that's going to give it that quadratic, that parabolic, that U shape on a coordinate grid. Okay, and these coefficients, that +5, the -4, the +1, they interact with this quadratic in some way to move it and change it somewhere around on the coordinate grid. So the technique I'm going to use is the universal solution technique. Basically, no matter what quadratic I'm given, I can always use this technique, and that's the quadratic formula. I just have one thing I need to accomplish before I can use it, and it's already kind of pre-accomplished for me in this case. I just have to make sure I have it in standard form on one side of the equation with the other side equal to 0. So that one's already pre-set up for me, so I can just jump right into the quadratic formula. If you had anything else over here, be it number or variable or whatever, I would just have to make sure I would take that object and move it, combine it with its corresponding like term over here on the other side so that I was left with the 0. So this can't look any crazier than what it already is. No parentheses, no other kind of arrangements. I would want it in this descending order in order to use my quadratic formula. And then at this point now it just becomes identifying what A, B, and C are. So let's go through that. A is the number that's attached to the x squared. So A in this case is the +5 that's multiplied by the x squared right there. B is the value, the coefficient that's multiplied by just the x, in this case the -4. Just be careful with making sure that you attach the sign to these coefficients. And C is the value that has no variable attached to it, in this case just the +1 there. Part of the reason why I want to make sure it's just equal to 0 on one side of the equation is if there was anything over here, one of these coefficients would be changing. Okay, so I know what A, B, and C are. Now I can apply it directly into the quadratic formula, that god-awful formula that we talked about in section 5. Okay, so hopefully it's written down in your notes, because as long as it's written down in your notes, you don't have to memorize it. But our quadratic formula says the following, and many of you have told me that you did, like you memorized it using the song. Great if you did. If not, just write down the formula, then you don't have to memorize it, or a song for that matter. So the quadratic formula says -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, again, that is written down in your section 5 notes. It's worth referencing on occasion, especially since it can be applied to solving any quadratic. But what we're simply going to jump to here is taking these a, b, and c values and plugging them directly into that quadratic formula. So the whole purpose of using the quadratic formula is that it will ultimately solve for x. I will get x equal some solution. And so I'm going to start with taking negative b. I always start with that negative sign. Some of you would jump right to just flipping the sign of whatever b is. In this case, I'm going to take the time to actually substitute in these values. Well, b is this -4 value here. So I have a negative version of that. That will end up being positive. Then I'm going to add or subtract the square root of a mess of stuff. So let's jump into that. And the first piece here will be just b squared. In this case, it will be a -4. So I'm going to take that -4 and square it or multiply it by itself. Then I will subtract 4 times a times c. Well, a in this case is that +5 out in front. And c is that +1 added on the back end. All of this mess will be over 2 times a again being that +5 out in front. So this, again, this method we covered in section 5. This is just simply plugging directly these 3 values directly into the quadratic formula. Even though it looks super complex, essentially all I'm doing at this point is order of operations, and just be careful about like negatives and stuff. All right, so simplifying this a little bit. All right, a negative version of b, or a -4, is going to give me +4. Plus or minus, the plus or minus represent the 2 possible solutions that can exist. Let me simplify what's underneath the radical here. So I would start with the b squared, which is -4 squared, or -4 times itself. -4 times itself, the negatives will cancel and I'll get +16. I'm going to subtract 4 times a times c, so I always take the time to do that subtraction, that minus sign right there. Now I'm going to do 4 times 5 times 1. 4 times 5 gives me 20. That 20 times 1 gives me 20. Some of you will be able to see it right now, but if I were to actually perform this next operation of 16 minus 20, I'll get a negative value underneath that radical, which is why I will get a complex solution in this case. But let's keep going just for the sake of it. All over 2 times a, 2 times 5 will give me 10 in the denominator. Okay, great. So far, nothing has really changed from what we've done in section 5 with the quadratic formula. So let's just keep pushing through. What we're going to find here is I simplify it a little bit further. Okay, I'm going to get x equals, and then that 4 plus or minus is still there. But let me simplify what's underneath the radical here. So just into a single object, 16 minus 20 is going to give me a -4. I'll deal with that in a second. It's all still over 10. Okay, so for the record, in section 5, when we talked first about applying the quadratic formula, if we ever got a negative value underneath the radical, we got the following result. We would get no real solutions. And that's still true here. There are no real solutions in this case. But in this section, we were tasked with finding the complex solutions, the imaginary solutions. So there's actually a simple thing to do here, and I'm going to show that in a second. But just to, again, recall us back to what we did in section 5, at this point in the past, we would have had no real solutions, because if I were to attempt to do this in a calculator, square root of a negative number, it would give me an error message. But now we're going to quickly deal with what to do here. So this is something that we did in section 6. So the front part of this stays exactly the same. 4 plus or minus, and the 10 on the denominator stay exactly the same. What is going to change here is this radical. So in section 6, we learned how to deal with this negative sign. So for the record, the square root of 4 now is going to stay the same. So notice I'm going to change this from a -4 to a +4. Okay, well, I can't just ignore that negative sign. What's going to happen here is now I'm going to introduce our imaginary number, I. This is what we learned in section 6. The simple transition here just says, like, all right, if I have a square root, a radical, the square root of a negative value, simply ignore the negative sign and add in the letter I. That's all that happened here. That's pretty much the summation of section 6 of how to deal with an imaginary number. Okay, at this point, now in section 1 of this chapter, we would have to deal with simplifying this radical. Thankfully, the square root of 4 is an actual simple solution. Square root of 4 is 2, right? But if it was anything that was a little more complicated, I would go through the same simplification process of first checking, is it a perfect square? This one happens to be. Or does a perfect square go into this value? Again, I don't have to deal with that here because 4 is something I can simplify. So my solution here, or solutions, plural, is going to be 4 plus or minus. Now, the square root of 4, again, is something I can simplify to just 2. And I cannot forget this I value. The reason I have to make sure I include the I is because fundamentally, I cannot change the fact that it was taking a square root of a negative. Okay? That is represented by this I. And it's still all over 10. So there my radical is simplified. This can actually simplify further. You may notice that each of these values is an even number, meaning that 2 can go into each of them. But more fundamentally, I could check to see, is there a common factor between each of these guys? If so, it can simplify. And this will simplify. 2 goes into each, so I'll factor out of 2, and that will give me 2 plus or minus. When I factor 2 out of 2i, I'm left with just I. And then when I factor 2 out of the 10 in the denominator, I am left with just 5. These will end up being my simplified solutions. Solutions, plural. Complex solutions, imaginary solutions. If you wanted to see these guys separated out into their 2 values, because again, that plus or minus kind of represents 2 and 1 right here, x equals 2 plus I over 5. And at the same time, it also equals 2 minus I over 5. That's what the plus and minus means. So these would be like the 2 separated answers. And I think some cases, Big Ideas requires that you separate them. So that's what that would look like here. That's what that plus and minus, how it would be separated. Otherwise, this is more the compact way of writing it. All right, let's do another one. So the thing to point out there is that nothing actually changed with the technique. And you can use quadratic formula for any of these quadratics as long as you have it in standard form set equal to 0. But nothing changed algebraically. The only thing I had to be aware of is as soon as I had a square root of a negative, just add in that letter I, and that's really the only thing that changed. All right. So our next one, we're still asked to solve, and now let's deal with one that I'm just going to really do this to apply a different technique, but we're given 4x squared plus 20 equals 0. Okay, so I'm going to use a different technique to solve for this one. The fact that it's missing an x term in the middle means I can apply square roots, which is to say we did this in section 3, where we isolate the x squared, and we want to isolate the x squared so we can take the square root of both sides and thus get x by itself, or solve for x. It'll be the fastest way in this case. But if you are the type of person that only wants to memorize one method, okay, and I get that. I used to be that way too. I didn't like have to learn a bunch of methods. If I was good at one, then I would just use that one and write it till I die, sort of thing, right? You can actually apply the quadratic formula to this guy too, but I'm going to rewrite this equation in a way that will be a little bit more helpful for me to understand how to apply the quadratic formula. And maybe you already know how to do that here, but let me make sure that for those that are interested, this is how you could use it. So I'm not going to change this formula at all, but I am going to add this other element that will come in handy. Okay, so these 2 different versions of the same exact quadratic equation are exactly the same. Okay, technically I did not need to write this 0x, but why would I bother doing that? If you were, again, the type of person that wanted to just learn how to use quadratic formula, that's a worthy one to choose because it's the same exact thing. There's no real difference in difficulty or anything like that. It's just order of operations over and again. You could use this for this equation, this quadratic equation. You would just have to understand that b, the coefficient attached to x, is 0 in this case. The very fact that it's missing, it's still technically there. It's just that the coefficient is 0. So if you were to apply the quadratic formula, a would still be the value attached to x squared. A would be a positive 4. B, even though there is no b term here, it still is technically there. It's a value. It's a real thing. It's just a 0. C is the value that has no x attached to it. In this case, it's the 20. That tends to be the thing that people would make a mistake on. They would be like, all right, well, that must be A, that must be B, and then C is 0. Okay, no, A is always attached to x squared. B is always attached to x. So the fact that it's missing here just means that B is 0. and c is the value that has no x value attached to it. Okay, so that'd be just something, if you wanted to apply the quadratic formula, that's how you'd have to set it up. But I'm going to use square roots because that'll end up being faster. So if I'm using square roots, my task here first is to get the x squared by itself. So I want to move the 20 away. I want to move the 4 away. So I would move the 20 by subtraction using its inverse operation since it was being added. And so here on the left, I'd have just the 4x squared, one step closer. On the right, 0 minus 20 gives me a negative 20. All right, not quite there yet. I still want to get x squared by itself, so I have to move the 4. The 4 is being multiplied, so I need to move it through division. And when I divide on the left-hand side, the whole reason I divided in this case was to get x squared by itself. And on the right-hand side, the negative 20 divided by 4 is going to give me a negative 5. Great. So far, nothing changed with the technique that we learned in section 3 about solving using square roots. At this point in section 3, what we would have come across is that if I ever had my x squared isolated and it equaled a negative number, there would be no real solutions here. That's still the case. This would represent a parabola that completely misses the x-axis. But again, I want to find the complex solution, so I will continue to solve at this point. And the way I would get rid of that squared is by taking a square root of both sides. This is where I'll run into a complex solution. On the left, I have the square root of x squared. That will get rid of the exponent here, equals the square root of the negative 5. Here again is where I'm going to get the complex solutions. Well, when I do this on the left-hand side, I'm going to be left with just x. All right. And when I do it to the right-hand side, when I take the square root of something, I get the plus or minus result there. I'm still going to get a square root here, but that square root is now going to be of a negative number. Again, if I were to attempt this on a calculator, it would spit out error messages, thus telling me that I have a complex result, an imaginary result. But we now know how to deal with that negative sign. There's actually a simple thing to do here where I convert it into a complex number, and that's to get rid of that negative sign and to throw in the letter I. So x here is going to equal plus or minus the square root of 5 times I. Technically, at this point, I would check to see, can this radical be reduced any further? Well, 5 is not a perfect square, and there is no perfect square that will go evenly into it. So this is as simplified as it will get. Just make sure you double check for that sort of thing, because that may pop up on a test hint. So technically, this would be the compact solution answer, the plus or minus version. If you wanted to split them up, my solutions here would be the plus version, or x equals positive square root of 5, which is an actual number. If I were to plug this into a calculator, it spits out like 2.24 times I. And at the same time, x also equals the negative version of that square root of 5. So that'd be like a negative 2.24-ish times I. Again, the I represents the imaginary or complex solution, representing the fact that there is no actual tangible place on the coordinate grid where it crosses the x-axis, but these are the imaginary solutions. Again, there is an application to that. You can trust me on that, but I'm not going to get too deep in it because it is pretty abstract. And that would be the solution to this one. I could have found the same exact thing had I used quadratic formula. For the record, I just had to make sure that b was 0 when plugging in. So, all right, so now we're going to do a little bit more of an abstract problem. So this one will be a little weird. The process is something that will be familiar, but still, it's admittedly a little weird. It's abstract. All right, so let me jump back to notes to show you this question. All right. So our job here is to find a possible pair of integers. Integers is a fancy way for numbers, positive or negative. Find a possible pair of numbers for a and c so that the following quadratic equation has two imaginary solutions. Okay. So this one is worded a little weirder than the things that we've done before. Pretty much the simple instructions before were simply to solve, right? In this case, there are actually going to be an infinite number of solutions. We just have to come up with one of the infinite solutions that will make it work. All right. So this quadratic equation, the fundamental thing to understand here is that even though I have this unknown a and this unknown c that I'm asked to solve for, so I have to solve for two different things here, whatever ends up here will be some sort of quadratic that can be graphed on a coordinate grid with Desmos or whatever. Okay, so that still represents the same kinds of quadratics we've been dealing now with 2 chapters. But I need to do it so that there are 2 imaginary solutions. What does that mean? Visually, that means that whatever this parabola will end up looking like on the coordinate grid, it has to completely miss the x-axis, therefore having no real solutions and instead having 2 imaginary solutions. Okay, well, that's what it would have to look like visually, just to understand what's happening. But how can I go about solving that? Here's the hint that I gave on the notes. This piece right here is actually something from what we learned in section 5 when it came to quadratic formula. And this may look familiar as far as that goes. B squared minus 4ac. In section 5, we learned that the name of this element of the quadratic formula is what we call a discriminant. Okay, it's the stuff underneath the radical in the quadratic formula. And what we learned in section 5 is that if that piece, and this will end up becoming some number solution, right? Some value, right? What's ever underneath the radical. If that element underneath the radical happened to be less than 0, which is another fancy way of saying negative, if this result happens to be negative, I would be taking a radical, a square root of a negative number, thus giving me imaginary solutions. So my goal here is whatever these a and c values equal, if this discriminant turns out to be less than 0, I will have 2 imaginary solutions. So that will be my goal. And you'll notice that I am given one of the variables, one of the coefficients, b. b will be -4 here. So let's apply that. So this is the quadratic equation I was given. ax squared minus 4x plus c equals 0. All right. So I do know what b is. B is a -4. I don't know what a and c are. My job is to come up with some combination here that will make two imaginary solutions be the result. Here is where I'm going to apply this concept. Whatever happens here, I do want b squared minus 4ac to be less than 0. Okay. The discriminant of this quadratic, even though I don't know 2 of the pieces, I want that piece to be less than 0. Well, I can plug in some of the stuff here, namely b is going to be -4. So when I plug in -4 for b, and I square it, I'm going to subtract 4 times a times c. Well, I don't know what a is. A is just a here, and same thing with c. C is just c here. I just know that this has to be less than 0, or negative. Well, I can simplify this guy a little bit further. Well, a -4 squared is -4 times -4, or +16. All right. Well, I'm still subtracting this unknown piece, -4ac or -4ac. This has to be less than 0. Okay. So I've simplified it a little bit, but I still have this. At this point, we're going to apply something from Math 1. In Math 1, we dealt with solving inequalities. This is an inequality. It's just not an equal sign. That's what makes it an inequality. But what I'm basically going to do here is I'm going to try and get this AC by itself. I'm going to move away the 16 and the -4 and see what it can tell me. So how would I move this 16? I would subtract that 16 from both sides of the inequality, just like I would any other equation here. I'm going to be left with -4AC on the left is less than 0 minus 16, which will end up giving me -16. Okay, well, now if I want to move this -4, the -4 is multiplying by the AC. So the way I would move it would be by division. Use the same color here. So dividing both sides by this -4 will move it. And I'll be left over with A times C on the left and -16 divided by -4. The negatives will cancel. I'll be left with a +4 on the right. Here is where that the importance of paying attention to Math 1 comes into place, because if you recall, if I were to divide both sides of an inequality by a negative, if I were to multiply or divide both sides of the inequality by a negative, something special happens to this inequality sign. It's going to change direction. In other words, instead of opening to the right, it's going to open to the left. And I'm left with this. AC, A times C, whatever A is, whatever C is, when I multiply them together, the result has to be bigger than 4. Let's think back to why this had to be the case. Again, my task here is to come up with a parabola that has two imaginary solutions. All that has to happen for this to be the case, using that discriminant rule, is that whatever A and C are, when I multiply them together, the result has to be bigger than 4. Well, there are lots of different numbers I can multiply together that are going to be bigger than 4. I just have to come up with 2 different values that make that true. You could literally pick your 2 favorite numbers, if you have favorite numbers, if that's a thing. But you could take any 2 numbers you want, as long as they multiply together, they're bigger than 4. That is a solution to this problem. The reason this type of problem tends to be so confusing to so many people is because there's not a single solution. There's actually an infinite number of solutions. So let me give you a case in point. For instance, if you decide, like, I don't know, maybe your favorite number is 8. Maybe it's your least favorite number. I don't care. Okay. But let's say you chose A being 8. As long as C was some number that when I multiply them together was bigger than 4, this is a true solution. So like maybe you see, you're like, I don't know, 2. Well, 8 times 2 is 16. Is 16 bigger than 4? Yes. Therefore, this is a possible solution. Is it the only solution? No. There are an infinite number of possibilities here. Decimals, fractions, whatever. I could come up with negative numbers. Okay. If A is negative 8, I would just have to make sure that C was also a negative number to make sure that they canceled so that my result here would be bigger than the positive. Okay. But there's an infinite number of combinations of numbers. This just happens to be one of those combinations that I can confirm. 8 times 2 is bigger than 4. So back in my original quadratic that was given, if I plugged in 8 for A and 2 for C, my equation would then read 8x squared minus 4c plus 2 equals 0. If I were to graph that on Desmos, I would come up with a parabola that completely missed the x-axis, thus having 2 imaginary solutions. It did not ask me what the 2 imaginary solutions were. All it asks me was to come up with some combination of values for these guys that created that result. Okay, a little abstract, but that's how you go about solving it. All right, let me go ahead and stop recording.